So just a quick recap of what we were doing so far. We defined what convex functions are, and we looked at some tests to check whether a given function is convex or not. Right? This included the first derivative test and the second derivative test. And after that, we looked at some sets corresponding to convex functions. The first was the level sets, which basically, so the level set S alpha is basically the set of all points in the domain for which f of x is less than or equal to alpha. And if f is a convex function, then the level set is guaranteed to be convex. However, the reverse is not true. Just because all the level sets of a given function are convex, it does not necessarily mean that the function is convex. Right? Then we defined what is called the epigraph for convex set, which is basically if f is a function in Rn, then the epigraph is a set in n plus 1 dimensions. Right? So it's the set of all x comma t such that t is greater than or equal to f of x. Right? And we saw that the epigraph being convex is a necessary and sufficient condition for f being convex. Right? And similarly, you can also define the hypograph, which is the set of all x comma t such that t is less than or equal to f of x. And a function f is concave if and only if the hypograph is a convex set. Okay, so these are sometimes useful tests to verify whether a given function is convex or not. Okay, and then we looked at this generalization in some sense of convexity of functions, which is called Jensen's inequality. So if f is convex, then and x is a random variable with any distribution for that matter, then f of expectation of x is always less than or equal to the expectation of f of x. Okay, and this holds for all distributions on R or more generally over Rn. All right, and Jensen's inequality has many useful consequences. We won't look at all the properties or applications of Jensen's inequality, but for example, if you're taking the information theory course, then you'll definitely see this again and again. So you can prove a lot of very useful properties of various information measures, including the entropy, KL divergence, and mutual information, just using properties that they're all essentially consequences of Jensen's inequality. All right. So now that we've looked at, or at least we've understood what convex functions are and some basic properties, let's go back to the original problem that we tried to solve, right? Where we want to formulate and solve convex optimization problems. Okay, so we'll go a little back and forth between convex optimization problems and convex functions themselves because they go hand in hand. Right? So in this class, we'll go back to the problem of formulating a convex optimization problem. We'll see what a convex optimization problem in standard form means. So we've already seen sort of a standard form of a convex optimization problem. We'll generalize it a little bit, and in the subsequent classes, we'll generalize it further, depending on what kind of constraints we can impose. And we'll see some examples of convex optimization problems. Okay, so sorry, so this is what we'll call the standard form of a convex optimization problem. So the goal will be to minimize some f of x subject to the constraints fi of x is less than or equal to 0 for I equal to 1 to up to m, and hi of x is equal to 0 for I equal to 1, 2, 3 up to t. So this is what I'll call the standard form of a convex optimization. Now, note that I could have written this equal. So I have two types of constraints in this case. I have inequality constraints, fi of x less than or equal to 0 for I equal to 1, 2, 3 up to m. But I also have explicitly, I'm writing out hi of x equal to 0 for I equal to 1, 2, 3 up to p. Now I can write an equality constraint as two inequality constraints, right? So hi of x is less than or equal to 0 and minus hi of x is also less than or equal to 0. But at least in this form, I'm going to write these two out separately. Okay, it's just a note convention that we will follow. Okay, but in principle, you could write everything using just inequality constraints. M and P could be any number, doesn't matter. It doesn't have to be the same. And all of these functions are f, fi, hi are all functions from Rn to R. Okay, so I have these two types of constraints, inequality constraints and equality constraints. Now first let's look at the constraint set. Okay, so I'll define the constraint set as the set of all x in Rn that satisfies all the constraints. Yes. Yes.
In this case, when we say I equal to 1 to so on till n,
Yes.
we imply that it's only up to the first n, right? But can it be, like, does it mean that I can be any one of those, or does it have to be all up to n?
Oh, all of them. So all of these. So for every I, fi of x should be less than or equal to 0. So f1 of x should be less than or equal to 0. F2 of x should be less than or equal to 0. Up to fm of x should all be less than or equal to 0.
M will be less than or equal to n.
It could be anything. Doesn't matter.
Yeah.
Right?
Yeah. Okay. I was confused. Like I thought those are just like parts of.
No. So remember, each fi is a separate function which operates, which is a map from Rn to R. Okay? So it's not, so they're not operating coordinate wise. Okay, so this is our constraint set. So the set of all points in Rn that satisfies all my constraints, right? It's an AND operation. So all of these constraints have to be satisfied. Okay. Sometimes this is also called the feasible set. So we can use them interchangeably. Okay, so and a priori we are not even guaranteed that the set is non-empty. Right? It could be the case that some of these constraints are not consistent. So it's possible that the constraint set is empty. Okay. Suppose that the constraint set is not empty or even otherwise, we'll define the optimal value for this optimization problem in the following manner. So maybe I should use something else. I'll say that f star is the infimum of f of x such that x is in the constraint set. So this is what I call the optimal value. Okay. So recall that I've not put any additional constraints on C. C could be bounded, it could be unbounded. We haven't seen anything yet. So, but irrespective of what happens, this quantity is always well defined. F star is always well defined, irrespective of whether C is convex or concave, or I mean, if it's whether it's convex or not, or whether it's bounded or not. If it's empty, that's a good question. We'll define F star to be infinity. Okay. In fact, we can even do the following. So given f of x and a set of constraints, we can redefine f. So I'll say that f tilde of x is equal to f of x if x satisfies the constraints, and infinity if x does not satisfy the constraint. This is sometimes called an extension of f. So now f tilde is defined over all of Rn. It may not be continuous and it may not be differentiable throughout. That's okay. But I still define it as follows. I claim, yeah, yeah. So this is how I'm defining it. Okay, irrespective of what f is. So given a function f and given a set of constraints which correspond to C, I define f tilde of x in this particular fashion.
So the question is,
yes,
x does not belong to constraint, always we define
I define it as infinity. Yes.
both for minimum and maximum.
Okay, so right now we're looking only at minimization problems. Okay, if not, if it's a maximization problem, then basically I'll define it to be minus infinity. Okay. So now this takes care of the previous question. What happens if C is empty, right? Because if C is empty, then f tilde of x is infinity throughout, right? For all Rn. And minimizing f tilde of x is the same as minimizing f of x. Do you all agree? Right? Because obviously if f of x is finite at some point, then those points will correspond to the minima of x. So the point which satisfies the constraints will definitely be a point of minimum. Okay, but otherwise infinity is going to be the minimum. Okay. But the interesting property of this extended value function or the extension is that if f is convex, then f tilde is also convex. Why is that the case? So you take any x1, x2 in Rn.
Assume that the domain of f is R.
Yeah. Now for f tilde, the domain is all of Rn.
Yeah, but for f in this case, we assume that same thing for this claim.
So we assume that f is certainly defined over C, right? Obviously that has to be the case. But outside C, it doesn't matter. I'm defining f tilde in this particular way, right? So that's okay.
So does this require the constraint functions to be convex as well, or they need not be convex?
Okay, yes, the constraints. So C should be a convex set. So if f is convex and C is convex, then f tilde is convex. Yeah.
By in the definition itself, CV define the domain of F to be between -1 and 1.
Sorry?
CV define the domain of F to be between -1 and 1.
Fine. Okay.
And we say we F of F to be x square.
Okay.
So in that case, when we take, for example, x equal to 2, which is not in the constraint set,
Yes.
then then the value becomes infinity. But
Correct.
then F tilde is not convex, right?
Why is it not convex?
There'll be a, like from 4 it goes to infinity directly, right?
Okay.
Like as we take 4 plus.
Okay. So
Defined. So say that it's convex or not in that case.
okay, let's see what happens. So when do you say the function is convex? So I understand the why it is intuitively confusing, because it seems now there's a discontinuity. So basically, if the discontinuity were finite, then you could obviously draw a straight line between 2 points, one before the discontinuity and one after, and the function value would be below this particular line joining these 2 points. Correct? That's the main issue that could potentially arise. Right. Because it's an infinite discontinuity, that issue doesn't arise. So let's take any 2 points, right? If both of these points are within the constraint set, then there's no issue at all. You agree? You always have theta times f of x1 plus, sorry, f of theta times x1 plus 1 minus theta x2 is always less than or equal to theta f of x1 plus 1 minus theta f of x2. So that's not a problem if both x1 and x2 are within the constraint set. Okay, and moreover, we've assumed that C is convex. Right? So any point in between the two, between x1 and x2, is also going to lie within the convex set, and it's going to be finite. Now, the only issue that may arise is if either x1 or x2 is not in C. Okay, so suppose x1 is not in C or x2 is not in C. It's also possible that both x1 and x2 are not in C. It doesn't matter. So on the left hand side, you have f of theta x1 plus 1 minus theta x2. Right? Now this could be finite or infinite, doesn't matter. On the other side, I have theta f of x1 plus 1 minus theta f of x2. And I know that either x1 or x2 is outside C. So what can you say about the right hand side? It's infinite, right? The left hand side, no, it's irrelevant whether what the left hand side is, right? Whether theta x1 plus 1 minus theta x2 is in C or not in C, doesn't matter. This is always less than or equal to the right hand side, because the right hand side is infinite. Right, sorry. So f tilde of theta x1 plus 1 minus theta x2 is always going to be less than or equal to theta f tilde of x1 plus 1 minus theta f tilde of x2, because either f tilde of x1 is infinity or f tilde of x2 is infinity. So it satisfies the properties of a convex function. Okay. But note that if f tilde were some function which has a discontinuity and it's finite everywhere, then this would no longer be convex. So right now we're looking at a function which has a discontinuity, but the discontinuity is sort of infinite. Right? On the other hand, if this discontinuity were finite, suppose I defined f tilde as f of x if x is in C and some finite value if x is not in C, then this function would be non-convex. You can prove it. In fact, any function which is finite valued everywhere and has a discontinuity is not going to be convex. Okay, so this is, at least in principle, useful because now f tilde of x is defined everywhere, and finding a minimum for x, for f of x over the constraint set is the same as finding the minimum of f tilde of x over all of Rn. Okay, and this will be useful later on. Right. So recall that I defined f star to be the optimum value. So it's infimum over all x and c of f of x. Now it's possible that this is never achieved, right? Or it's also possible that this is achieved at a single point or at multiple points. But nevertheless, I'm going to define x opt as the set of all optimal points. And we say that so if the set of all optimal points is not empty, then we say that the problem is solvable. Yeah.
The suppose the minimizing value was something like minus infinity.
Yes.
Then would we say that set of all optimal points is empty or not? Then no particular point achieves minus infinity. And then f of x is minus infinity.
Then we say that it's not solvable. So I want a point in Rn which satisfies this. Basically, yeah, so I can't find x within the constraint sets that this is satisfied. Okay. Now, sometimes we're okay with not getting an optimal point, right? For example, if we run an algorithm such as gradient descent, you're not guaranteed to reach the optimal point, but after a certain number of iterations, you can say that you're sort of roughly close to an optimal point. So we'll say that a point is epsilon suboptimal so we say that it is epsilon suboptimal if f of x minus f star is less than or equal to epsilon. Right? So remember that f of x is always greater than or equal to f star because f star is a minimum value. If it is epsilon close to the minimum value, then we'll call it epsilon suboptimal. And many numerical algorithms that you will use for getting for solving convex optimization problems are only guaranteed to give you some epsilon suboptimal point. So, so for example, if you take
Should that be f of x optimal?
which, so it's f star, right?
X value of function. F.
You mean this one? So it's okay. I'm saying that this point x is epsilon suboptimal if f of x minus f star is less than or equal to epsilon. Now, it's possible that f star cannot be achieved, right? I'm defining it as the infimum of f of x. Unless you have some nice conditions on f and c, you're not guaranteed that there exists a point that achieves this. Okay. So for example, let's take f of x equal to minus x. Minus x. Okay, it's a convex function. It's basically linear, right? And what is the minimum? What is the minimum of minus x? It's minus infinity, right? But can you achieve f star? You can't, right? It's a problem that's not solvable. Can you get an epsilon suboptimal point? No, you can't. Right? So this is an example where you cannot even achieve an epsilon suboptimal, right? But on the other hand, suppose I take f of x equal to e to the minus x. Okay. So the first example was f of x equal to minus x. So this problem is not solvable. Let's take another point, f of x equal to e to the negative x for whatever x. So the one constraint is that x is greater than or equal to 0. It doesn't, you don't necessarily have to put this constraint, but fine. So what is f star in this case? F star is 0, right? Can you, is there a point in R for which f of x equal to f star? No, right? So again, this is not solvable. But then can you find an epsilon suboptimal point? You can, right? So no matter how small you make epsilon, you can always find an x for which f of x is less than or equal to epsilon. Okay? And if there could potentially be multiple points which contain multiple epsilon suboptimal points, right? In this case, it would be sort of an interval beyond a certain point. So that is what we call the epsilon suboptimal set. Now, particularly when the given function is non-convex, you can't always find the global optimum, right? So in those cases, we're just satisfied with local optimum. And we define a local optimum such that, so a point is said to be a local optimum if every point in its neighborhood takes a value above or greater than the value that this local optimum takes. So we say that some x star is a local optimum of f if f of x star is less than or equal to f of x for all x in some neighborhood right? So in other words, we say it's a local optimum if there exists some epsilon for which this happens. Okay. Now, even among constraints, right? So we saw that there are two types of constraints: equality constraints and inequality constraints. We'll again use some terminology for each of these. So suppose we're given some constraint fi of x is less than or equal to 0. So we say that this constraint is active if the point x is such that fi of x is equal to 0. And it's inactive otherwise. Okay, so we're only looking at points which satisfy the constraints. Okay, so for example, if you take a set of linear constraints, okay, each linear constraint basically defines a half space, right? And the set of all linear constraints basically defines some kind of a polyhedron, right? So at any edge of the polyhedron, so any face of the polyhedron, you have your one constraint would be active. Suppose you're looking at 3 dimensions in R3. The constraint set would basically be some kind of a polyhedron. At any face of the polyhedron, exactly one constraint is active, right? Because it's satisfying only one of those constraints, because it's at the boundary of those constraints. So these active points essentially correspond to points on the boundary of your constraints. But along an edge in R3, two constraints would be active, correct? Because it's exactly at that point where equality is satisfied for two of the constraints. At a vertex, at least 3 constraints are active, and so on. Right? So sometimes you also have redundant constraints. Right? Suppose that you're given a set of constraints, and removing one of the constraints does not change C. Then that constraint is said to be redundant. You can just get rid of that.
Space within block.
Yeah. So for example, I give you, say, x1 x set of all x1 x2 such that x1 is less than or equal to 0, x2 is less than or equal to 0, and x1 plus x2 is less than or equal to 1. Right? So x1 less than or equal to 0 and x2 less than or equal to 0 basically puts you in the third quadrant. Right? x1 plus x2 less than or equal to 1 is a straight line which basically at least partially passes through the first quadrant. Right? It includes all of the third quadrant. So in general, given a convex, the convex optimization problem essentially corresponds to finding the value of f star and at least one point which achieves the optimum value, okay, if one exists, right? So now suppose that I define f of x to be 0 everywhere, subject to certain constraints. Then do you think this problem is useful at all? Okay, so I define a problem. We are given set of constraints, so minimize f of x subject to, again, fi of x less than or equal to 0, hi of x equal to 0, with f of x to be equal to 0 for all x.
Finding C might be hard.
Finding
C might be hard.
Okay, I mean, I'm not worrying about the complexity or something, but is this problem useful? Is the
So the problem might be useful.
Correct.
Problem itself might be interesting if finding C is hard. Like,
correct. So to put it more precisely, so this essentially corresponds to finding whether there's a point which satisfies the constraints, right? And sometimes that itself could be a hard problem. Finding whether there exists a point, whether the constraints are consistent or not. Right? And this is sometimes called a feasibility problem. Yeah.
See, there is a set of constraints,
Yep.
and removing one of them doesn't change C.
Correct.
But it is possible that removing the constraint can actually change the optimum within the C, right?
It doesn't, right? Because again, the constraints themselves are not relevant, right? If you're already specified C, you're trying to minimize f over C. So whether you're presented C in the form of those constraints or in any other form, it doesn't change the optimum value or the point that achieves the optimum. So this was just a quick introduction to some terminology, right? Just the basics to get us started with formally analyzing convex optimization or optimization problems in general. So now let's look at some examples of convex problems that arise in different applications and are in fact convex optimization problems. So we'll see that some of them are equivalent to problems that we've seen before in one setting or the other. Okay, but before that, maybe we'll have a quick quiz. Okay, anyone doesn't have their cell phone? Okay, can you take a piece of paper? It's not connecting. Okay, then can you all take a piece of paper and Please write your name and roll number. Yeah. So the coordinate includes the axis as well. So these are not disjoint, but rather this includes.
Sorry, two questions.
Just two questions.
Do we need to write the question?
No, you can just write the answer.
Yes, no chemistry.
It's well, if it's option, write all the answers which are correct for each question.
You write all the options as tick.
Whatever, anyway you feel more comfortable. As long as it is clear to me what your answer is, that's fine. No proof, just the answer. Yeah. The first question is A is a subspace, convex, cone, proper cone. Second question is the dual of A is first quadrant, second quadrant, third quadrant, fourth quadrant. That's okay. You can not collect and give it. Is everyone done? Anyone who is not done yet? Okay, can you all collect and so what is the answer to the first question? So it's a convex proper cone, so it's also a cone. The dual of A is second quadrant itself. Okay, so now let's look at a concrete example of an optimization problem, and one that is very basic in statistical estimation. So what is the problem? The problem is as follows. There is some parameter or there's some quantity that we want to find out, right? We want to know what is the value of x. X could be in R, it could be in Rn, something, right? It's some parameter that we want to estimate, but we don't have access to x. We can't get x directly. What we instead have is some quantity y which is related to x. And how is the relationship between x and y defined? It's through some conditional distribution. So you can view y as some noisy or some transformed version of x. Okay, so y is your observable, and x is the parameter you want to estimate. Right? And this covers a very broad class of problems. Right? For example, it could cover things ranging from, say, digital communications, where you're transmitting something through a noisy channel. So the observable is what you observe at the output of the channel, what the receiver gets, and x is actually what was transmitted. So the goal is to infer what was transmitted from what is received. This could also cover something like object detection in an image, where x is whatever the object that could be present or not present, and y is sort of the image or what you observe. So, but one key assumption that we will make throughout is that we know this relationship between x and y. So py given x is given to us. I'm going to use Py given x to denote either a conditional PMF or a conditional PDF, depending on whether x and y are PMFs or PDF. So we'll generally look at probability density functions, but I'll still use the notation Py given x instead of Fy given x, because f is going to typically denote the function that we're trying to optimize over. Yes.
Communication.
Yes.
So this Py given x.
Correct.
It is obtained through some measurements or
It's typically, so you have a model for the system, standard, depending on what kind of a channel that you have. So for example, in point-to-point wireline communications, you generally assume that Py given x is it's basically a conditional Gaussian. So y is equal to x plus Gaussian noise. That's the standard assumption. Or if it's some kind of a wireless channel, let's say line of sight, then y is equal to h times x plus noise, where this h is what is called a fading coefficient.
but in the case of machine learning, these are all trained data is what.
Correct. So again, that's why we are making this assumption that we know Py given x. Now, typically in whatever data-based learning or data-driven learning, we don't have access to Py given x, but instead we have, let's say, pairs of x comma y. So one way is, of course, to learn or get a good estimate of Py given x, and then that's typically what you try to do in data-driven learning approaches. Right? But now we will assume that we know Py given x. So suppose we're presented with this, then what is a good estimate for x given y? And the way you formulate this problem, in fact, determines what your solution is and how easy or difficult it is to obtain a solution. And again, there are different models for this. One wherein x itself is assumed to be random and you know the distribution of x. The other case where x need not be random, it's some fixed quantity, y is random and you observe y. Okay. So let's start with the case where x is also assumed to be random. You know x, you know px, and the goal is to estimate x from that. X is fixed but unknown, right? All you know is that x belongs to some set, and that's about it. So again, the problem is not fully specified yet, because I've not told you what constitutes a good solution to this problem. So for now, we'll relax this assumption, but x is random and x is distributed according to some density that I'll call px. So now let's again make another relaxation just for now, that x and y are discrete. Okay. Again, we'll formulate it in the most general form, but just to get intuition, let's try to pick x and y discrete. And the goal now is to get is somehow estimate x from y. So I want an x hat y, for which minimizes the probability of error. Okay. So the goal is to design some x hat of y such that the probability that x hat is not equal to x is minimized. You can use. Okay. You can use continuous theorem also. You can use base theorem. That's fine. Yeah. Correct. So I mean, for the continuous case, even the probability of error does not really make sense, right? Because the probability that x is equal to one particular value is 0. But first, let's write out this quantity. Right? Okay, but maybe before that, I'll give you what the solution is. So do you know what the solution to this is? P of, okay, so the claim is x hat of y is equal to P of argmax P of y given x times P of x. In fact, this is the same as taking argmax over x Px given y. Because y is fixed. I mean, you got this from base theorem using this particular approach, but effectively it's just the argmax over x of Px given y. Has anyone not seen this before? Okay, so this is what is called the map estimator. Or the maximum a posteriori estimator. And why does this minimize the probability of error? So, okay, so even before that, let's just look at this. Basically, what are we doing? Given, let's look at this particular expression, argmax over x, P of x given y, right? So, what does this tell us? So, you're picking the x which is most likely given the observation y, right? What is the most likely x given y? And that is going to be your map estimate. The claim is that this also minimizes the probability of error, which is intuitive, but how do we prove this? No convince. Everything is discrete, finite alphabet, so it's easy. Okay, what is the probability of error equal to?
Probability of summation times in error. Average probability. You can take the average probability over.
Okay.
You take mean probability. So that will be the actual error times the probability of that x. Because to 1 minus summation over probability of x.
Yeah. So the easier thing is to write the probability of error x hat not equal to x as 1 minus the probability that x hat equal to x. So 1 minus the probability that you're correct. So trying to minimize this is the same as trying to maximize probability that x hat is equal to x, right? But what is this equal to? Is this it? Yeah. Okay, there's one way to do it. You can say that, so you only count those xy for which x hat is not equal to x. Sorry, x hat is equal to x. But what is this equal to? This is p of x hat of y comma y, right? Because it's 1 only if x is equal to x hat of y and 0 otherwise. So it's just p of x hat of y comma y. And the goal is to minimize this, or in other words, maximize this. So I can write this as 1 minus summation over all y, p of y, p of x hat of y given y. And I want this quantity to be the maximum. So I might as well choose x hat to be the argmax of px given y. That indeed maximizes this particular quantity. Yes. Sorry, can you repeat? Yes. Doesn't matter, right? So we want to minimize the average probability of error, correct? But for every y, if we choose x hat to be the one that maximizes px given y, then this overall quantity is also maximum. Okay, so the map estimation problem generally is you find maximize p x given y or px comma y, right, over x. Now at times, instead of maximizing the probability distribution p of x comma y, you instead look at log of p of x comma y, because maximizing p of x comma y is the same as maximizing log of p of x comma y, and that is called the likelihood. So this p of x comma y, or p of y given x, is sometimes called the likelihood function, and log p of y given x is called the log likelihood function. Any question? So the map estimation problem is one of maximizing log p of x comma y, or which can be written as log py given x plus log px. There's a reason why I'm writing it in this particular fashion. We'll see that a little bit later. Uh, but remember, you're maximizing it over x, right? I'm writing it as the log likelihood function plus some other quantity. Okay. And if log py given x is a convex function, or log of p of x comma y is a convex function, then this turns out to be a convex optimization problem, right? And these distributions, I'm sorry, I should take a step back. So if log p of y given x is a concave function, because after all we want to maximize this, then this becomes a convex optimization problem, right? And those distributions for which log of p of y given x or log of p of x is concave, so these are called log concave distributions. So if I take the Gaussian p of x to be e to the minus x squared by 2 is this a log concave distribution? Yeah. So if I take log of this, log p of x is just, let's assume that we're taking to base e. This is going to be minus x squared by 2 minus log root 2 pi. This is just a shift, right? What about minus x squared by 2? Is it concave? It's a concave distribution. So it's a log concave distribution. What about the distribution p of x is equal to e to the minus mod x divided by alpha divided by 2 alpha? Uh, yeah, it's a Laplace distribution. Is it log concave? It is. What about p of x being the uniform distribution? So we'll define log 0 to be minus infinity. Yeah, this is also log concave. So as long as you have to maximize a you have to maximize some kind of a log likelihood function where the distribution is log concave. This effectively amounts to solving a convex optimization. So maybe this is a good point to stop. Let's continue on Monday. Any questions so far? Okay, so then let's stop. So this is chapter 3, yes. So what is I don't remember the exact chapter numbers, but convex functions, this parts of it is taken from the chapter on convex optimization problems, but there's also a separate chapter on statistical inference, statistical estimation problems.